Welcome, everyone. In today's explainer, we're putting on our detective hats to investigate the hidden nature of the everyday stuff all around us. We're diving deep into the secrets of mixtures.
So, here is our game plan. We'll start with mixtures and their types, then unlock the secret of the Tyndall effect, see how solubility plays with temperature, and finally, look at how we can tear these mixtures back apart. Let's get right into it.
Section 1. Mixtures and their types.
Right, so what actually is a mixture? Well, think of mixtures as physical roommates, like oil and water. They share the same space, sure, but they can always be separated. Compounds, on the other hand, like H2O, are chemically locked together. You can't just pull them apart with simple physical tricks.
And we can break down these physical combinations into three distinct groups. There are solutions, which are blended perfectly, suspensions, where you can literally see chunky particles floating around, and colloids. Now, colloids are tricky. They look perfectly mixed, but they actually have hidden particles suspended inside.
Which brings us to Section 2, the secret of the Tyndall effect.
To see what's truly hiding in our seemingly clear liquids, we're going to use a laser pointer. If you shoot a laser through pure water, absolutely nothing happens. The beam just passes straight through invisibly. But hit a beaker of water mixed with chalk or milk, suddenly you see this bright, glowing path scattering the light.
What's happening on a microscopic level here is just awesome. Those tiny chalk and milk particles are essentially doing a microscopic disco dance in the water. They're constantly bouncing around, reflecting that laser light straight into our eyes, proving they aren't truly dissolved.
Now, before we start testing the physical limits of our mixtures, we have to know exactly how crowded they are. We measure this with concentration. It's basically a simple percentage. You just take the amount of your solute, say sugar, and divide it by the total solution. It tells you exactly how densely packed your mixture really is.
All right, Section 3, solubility and temperature. Let's find those limits.
To find a mixture's breaking point, we have to talk about temperature. I mean, have you ever wondered why your favorite soda goes completely flat when you leave it out in the hot sun? It's all because of the totally contrasting rules of solubility. Heat works wonders if you're trying to dissolve more solid sugar into a hot tea. But for gases, it does the exact opposite. Heating up that warm drink literally forces the carbon dioxide gas right out of the liquid, leaving your soda completely flat.
Moving on to Section 4, separating the mixtures.
First up in our toolkit is crystallization. By taking a hot, supersaturated solution and drastically dropping the temperature, the liquid simply can't hold on to the solid anymore. It literally kicks out pure solid crystals, leaving all the unwanted impurities trapped in the leftover water.
But what if you have two liquids that are perfectly blended together, like acetone and water? You can't exactly freeze them apart. That's where distillation comes in. This trick exploits their totally different boiling points, literally boiling one liquid away before the other even gets close to turning into a vapor.
There's a catch, though. For simple distillation to work without both liquids evaporating at the exact same time, their boiling points need to be separated by a gap of at least 25 degrees Celsius.
So, walking through it, we heat up the flask, and the acetone vaporizes first, at about 56 degrees. That vapor shoots up, hits a cooling zone called a condenser, turns right back into a liquid, and then pure acetone drips smoothly into a brand new container. Pretty neat, right? Next, we have paper chromatography, which is just an incredibly elegant method. Water climbs up a piece of paper through capillary action, and as it woes up, it drags a single ink dot along with it, separating out all the hidden color pigments, based entirely on how soluble they are in the climbing water. Finally, for certain heterogeneous mixtures, we have a process that sounds like pure magic: sublimation. This is where solid substances, like camphor, skip the liquid phase completely. You heat them up, and they transform directly from a solid straight into a vapor. No melting required. So, as we wrap up today's explainer, I want to leave you with a quick thought to spark your inner scientist. Take a look around you. How many supposedly pure, everyday items sitting in your house right now are actually secret mixtures just waiting to be separated? The world is full of them. Keep questioning and keep investigating.